Hey everyone, just give me a second. I'm going to try to make it so I don't hear the beeps all the time. Yeah. All right, whatever. I can't figure out the chime. So yeah, I'll just start recording now. I think yeah, we have about 60 students here, so there are still what 90 missing then, but who knows? Maybe if they've just learned the whole course on their own. Okay, so let's record. All right, cool. So yeah, this is just the review session for the exam that's coming up on Friday. So I'll basically just review the content that we've covered already in the course. This is pretty hefty since it's a bit later. This exam includes most of the important material from this course, and it's worth almost twice as much as the other exam, right? So this exam, I think, is worth 35% of the grade, and then the exam two is only worth 20%. So it's not a very good exam to bomb, but it should be okay as long as you just apply yourself. So basically, what are we going to cover? Oh yeah, just as a kind of intro. So the exam isn't going to be in our normal classroom. There's just not that much space in it. We would basically just be shoulder to shoulder. So it'll be in this massive chemistry lecture hall at the west side of AQ, basically. It's just one of those enormous rooms, right? So it's just C 9001. Um, so yeah, I guess I'll talk. Like I didn't write the exam. I don't know what's on it. I don't know any details, but I've been TAing for Daniel for quite a while. So I can kind of talk about some strategies a little bit. The biggest thing here is just what I highlighted. This is a short exam, right? This is just 100 minutes. And generally, Daniel writes lots of questions for the exam. So like something reasonable for 100 minutes, I don't know, maybe like 5 questions would be reasonable, but you might get like 9 questions, right? So the biggest thing with this exam is just time management. It's open book and open note and everything. So you can have like a textbook, you can print off all the assignments, all the solutions, all the lecture notes. But like, sure, that would be fine if it was like a 3 hour exam, you could just copy everything down. But the fact that it's only 100 minutes, if you don't really know what you're looking for or you're struggling on a question, you don't have time to solve it yourself. So yeah, as you're preparing for this exam, just keep that in mind. Learn how to do all of these questions quickly, right? Especially when you're going for part marks and you don't really understand it. Don't spend half an hour if you're just going to get like 2 out of 10 part marks on something by writing nonsense, right? So, yeah, just really mind your time, right? So, open book, open notes. I think the limit was like 600 pages, 1,000 pages. He doesn't want you to bring like multiple textbooks in, but it doesn't matter. No electronics at all. So no calculators even. Just you don't really have to stress out about calculations. It's fine if you just leave stuff as like a square root of three. You don't have to compute what square root of three is. Um, yeah, most numeric things they'll kind of end up working out fine as long as you've gotten the correct answer. But yeah, don't worry too much about it. As long as you put stuff into a form where you could compute it with a calculator, then yeah, just leave it in that form and that'll probably be good. But most of these questions aren't really number questions anyway. They're kind of like charting, designing, stuff like that, right? So yeah, I've underlined this. This is really important. So when you're going through this exam, just make sure you actually answer every question. So I mean, this isn't it's not that hard of a course, but it's not such an easy course either, and students fail it every single year. The reason they fail is mostly because they leave questions blank, right? If you leave a question blank, you get zero for it, right? At least attempt something. You can get some part marks. Don't write like pages and pages of nonsense because you'll probably get the same part marks as if you just wrote like a short half page of nonsense. But just read the questions carefully and then make some reasonable attempt at completing them. It's fine if you're on the wrong track. It's fine if you kind of have misunderstandings, but at least put an effort in because, yeah, I mean, if you leave half the exam blank, there's no way you're going to get more than 50%. Do you know what I mean? So, yeah, that's the main thing. It's just good time management and answer every question. So yeah, beyond that, I don't really know any details about the exam. Are there any questions just related to that though? All right, cool. It seems like no. So, we'll go straight into the review then. So, I've kind of listed these five areas that are pretty important that we've covered in the course so far, right? So, the very first class is the one that I taught, and we kind of went through lots of stuff. It was mostly like a Fourier transform review, right? And the main thing with that is just the distinction of different signal types, right? So the biggest difference in two types of signals in this course is definitely between power signals and energy signals, right? So energy signals are just any signal that has a finite energy. So you take the signal, you square it, and then you integrate it from negative infinity to positive infinity, right? Um, that would be just the energy of it. It's not energy in the sense of like joules, like volts. It's really just V squared integrated over time kind of energy, right? But it basically, it if the signal has some finite energy, if you square it and integrate it over all time, then we call it an energy signal, right? So that'd be something like, just the sound of your hands clapping once, right? It's quiet before that and it's quiet after that. So there's only the energy of the one clap. So that's like an energy signal, right? Um, any signal that repeats, though, it's going to be a power signal because any signal that repeats is going to have an infinite amount of energy because you're just going to add it up every single clap. Eventually, the energy will just go to infinity. So that's a really big distinction in this course. We're often looking at periodic signals and those repeat forever. And then you're not ever going to analyze the energy of those signals. You're always going to analyze the power because you can still do the integral, you can still square the signal and integrate it, but you're not going to integrate it really from negative infinity to positive infinity. Or if you do, you're going to be dividing by the span that you integrate by to get the average power of the signal, right? So yeah, that's a super important distinction in this course. So I won't go through the slides on that because it's pretty basic, but just remember that you have different equations, different tools for power signals versus energy signals, right? Um, so yeah, the other big distinction between um, signals here is periodic signals that repeat versus signals that don't repeat. So periodic would be something like a sine, right? Sine wave will just keep going up and down, up and down, up and down forever. So that'll be periodic. An aperiodic signal would be something like a sinc, like a sine x over x, right? So that kind of like fades in and then fades out, and it never actually repeats. So it's totally different. Arshia Mohammadi, do you think the Lab 2 material might show up on the exam? Yeah, I think probably. There's a good chance it will. Yeah. So yeah, we have the periodic and aperiodic. The main difference with these is just that we use different tools, right? So just remember, anytime we have a periodic, we use Fourier series. And otherwise, we use Fourier transform, right? They are basically the same thing, except Fourier series. We only actually take that integral over the specific harmonics of the fundamental frequency, right? Because any periodic signal can be represented just as a sum of different sinusoids at multiples of its fundamental frequency. And anything else, we basically take the inner product transform with respect to any frequency, right? So, like, basically, you take the Fourier series of some kind of a periodic signal, and it could look like anything, right? It could something like low pass might look like that, but you see, it has some value for every single frequency, like F1 or something. You take the Fourier series of a periodic signal, it doesn't look like that at all. It literally only has impulses, and they could be like really any size, but they're only going to be at multiples of the fundamental frequency, right? So yeah, we deal in this course with lots of periodic signals, lots of aperiodic signals, right? We just use these different tools. They're almost the same thing, but it's just really about which frequencies are worth caring about. And with periodic signals, you only care about the frequencies that are multiples of your fundamental, right? And then, yeah, I guess what else we have for signals is just we can express signals in either time domain or frequency domain. So usually we always start off in time domain. Say you have a recorder or a microphone. It's just measuring the air pressure over different times, right? But a lot of the work we do is in frequency domain, right? So what we do is rather than represent the signal as just different values in time, we represent it at different values in frequency, right? So these are equivalent. We can either have a different amplitude at each time, or we can have a different amplitude at each frequency, and they end up representing exactly the same signal. So we lose really nothing. And a lot of the analysis that we want to do is easier in frequency domain. Um, it's a little bit tricky sounding, but it's really just because complex exponentials are the eigenfunctions of linear time invariant systems, right? So they just let us do much easier analysis, right? So that is the quick breakdown of signals and distinctions. Are there any questions about that or Fourier kind of stuff? All right, cool. So yeah, I guess let's just jump right into the content. So the first part of the course and a pretty big part of the course was on amplitude modulation, right? So with amplitude modulation, the main idea is that we have some kind of high frequency sine wave or cosine wave, and we're just transmitting information by changing the amplitude of it, right? So the really big deal here is that we have quite a few different forms. We have dual sideband with full carrier, or it's called AM in this course. We have dual sideband with suppressed carrier. It's called DSB in this course. And then we have two types of single sideband. So you really need to know all of these different forms, especially single sideband. It's pretty important, and it almost always comes up on the exams. Just and if you guys haven't been like coming to class or following the lectures or something, if you try to solve a single sideband question on the exam and you haven't seen one before, there's no chance. Like that's not something you're going to figure out how to do during the exam. So it's good to at least cover those slides, understand some Hilbert. And then we have two little concepts as well with AM. We have the difference between coherent and non-coherent detection, right? It's basically about how expensive our receiver needs to be. And then we have the concept of quadrature, where um, in the same frequency band, we can actually transmit two completely different signals, right? And that's just based on whether we use a sine or a cos. So that is the main thing. So I'll just move over to the notes here. Share. Is it this one? All right. This is for DSB, Albert. All right, cool. So yeah, I guess this will serve as a decent slide deck. So this is the from lecture 4. So the main thing is that I wanted to talk about is here's the basic form of amplitude modulation. That is where we have this like radio frequency, a high frequency cosine here at carrier frequency FC. And the way we transmit information is we just change the amplitude of it. So it's basically going to go between AC times 1 plus KA times our message. No, it's just always going to be that. So depending on the message value, the actual amplitude of this cosine is going to be changing, right? So there are quite a few important things to realize about this, and I think most of you were still coming to class when we covered this, so I won't go through it I mean, I won't spend too much time on it. This 1 plus is a huge big deal. So with ordinary amplitude modulation, and this does not apply for DSB, suppressed carrier, or for SSB. For ordinary amplitude modulation, we never let the amplitude go negative. All right. The reason for that is just you guys have kind of seen it, maybe if you've looked at Lab 2 so far, but the cheapest way to demodulate an AM signal is just to hop from peak to peak. So let's just say that we actually have like an AM signal. So it has some nice amplitude here, and then it goes to a small amplitude, goes to like a big amplitude again, right? So a really cheap demodulator is just a peak detector, and it just hops from peak to peak basically, right? So if we want that to be the message, you see, we need to keep it always in the positive half because if the amplitude ever goes negative, it's going to try to track these peaks on the bottom, but it won't. It's going to catch the peaks on the top still, so there will be distortion. So remember, the whole point of this 1 plus in ordinary AM is just to prevent overmodulation and make sure that this amplitude is always positive for the cos, right? So the only real distinction between that and dual sideband you can see here is that we have no 1 plus. We just literally multiply the message exactly as it is by the cos. And now the message will be either positive or negative, right? So that means the amplitude will be either positive or negative, and really it means we just cannot modulate cheaply like this. It says right here for demodulation, we require coherent detection, right? And it's just more work, basically, right? So yeah, that is the two really basic types of AM. The important thing to, I guess, figure, and I mean, for your exam, you guys need to bring in your own formula sheets and everything, right? So you should have as many useful equations as you can on them. So for sure, include the prototype form for ordinary AM and for DSB. And for AM, you want the power efficiency equations as well. So those are in the previous slide deck, maybe 2 or 3. And the main thing is when we actually modulate something with AM, we end up with a whole bunch of power at the carrier frequency and some power at the sidebands, basically. This power at the carrier frequency conveys no information at all. It's literally just the product between this +1 and the cosine. So that's entirely wasted power, right? So the equations in those previous slide decks that you'll need for that and that you've already used in the lab one. Basically, they only matter for AM, right? For this with dual sideband with full carrier. They don't matter for dual sideband suppressed carrier or for SSB, right? There's always just going to be perfect efficiency for those. But yeah, for ordinary AM, you guys will need to know the power efficiency calculations. And you can just figure it out. Figure out how much power is from this +1 versus how much power is from the Ka times m of t, right? So yeah, these are the two really basic types of modulation, and then we go into the trickier types, which are single sideband. But I think before that, I'd wanted to discuss some quadrature. Let's see. Yeah, let me find out where the quadrature stuff is. Oh, let's see, right here. Okay. So one weird thing about AM is that if you try to modulate with a cosine, right, and then you try to demodulate with a sine wave, so 90 degrees out of phase, you end up getting nothing, right? Um, it's kind of a bit of a disaster. We can see it on these really important trig identities here. So these are the most important trigonometric identities in the course. In this course, we're always just multiplying sinusoids by each other, right? So cos times cos, that's basically what we get with amplitude modulation. You see, we get cos at the sum and a cos at the difference and whatnot. Sine times sine, it's all kind of good. So the main problem is when we multiply a sine by a cos and they're at the same frequency, um, this term here becomes a problem, you see. Um, we end up getting, so say alpha and beta are both like 2 pi fc times t. If we multiply a sine by a cos, we get this one sine at like 4 pi, like double the carry frequency, 4 pi fct. And then we get sine at 0, and sine at 0 is 0. So that's a pretty big problem because um, when we modulate or demodulate, we end up filtering this one out and we only keep this one. So you can just see from this sine times cos trig identity that if you try to modulate or demodulate a signal with a sine when you modulated it by a cos, you end up multiplying the message by 0 in the end, right? Compare that to what we do if we try to demodulate with the same cos that we put in. We get this term here will be at double the carrier frequency. So this would be way up at 2fc because it's alpha plus beta. And then this one here will be at 0 because alpha and beta are the same. But cos of 0 equals 1. So what we end up getting when we demodulate this message, we end up getting like our actual message multiplied by 1 instead of by 0. So just from these kind of grade 11 trig identities, we see how terrible it is if we modulate a signal with a cos and try to demodulate it with a sine, right? But it's also an opportunity for us because we can actually combine, we can modulate one signal with a cos and we can modulate another signal with a sine, both with the exact same frequencies. And then this one here tells us that they won't interfere with each other, right? When we try to demodulate the combination with a sine, we only get the term that was modulated with a sine. And when we try to demodulate that signal with a cos, we only get the term that was modulated with a cos. So that's the real key to quadrature as well as single sideband. It's the key to lots of this stuff, really. So if we go back, see, here is quadrature amplitude modulation, right? So you see we have the one single AM coming out, right? This SFT. So normally what we would do is we just take our message, our M1 for dual sideband, and we just multiply it here by the cos, right? And then that's it. But you see with quadrature, we have the option of also adding a completely separate message down here, M2. We don't multiply it by cos, we multiply it by sine, right? And then we add together and we get this transmitted wave here. And you see they're both at the same frequency. One's at FC and the other one's at FC, but it's perfectly fine. They're actually not going to interfere with each other. If you want to M1, you just have to demodulate it with a perfect cosine. Then if you want M2, you just demodulate it with a sine instead, right? And it just needs to be exactly in phase. Your cosine needs to be in phase with the cosine. Your sine needs to be in phase with the sine. And then you can split this modulated signal into two different demodulated signals, right? So the math here is actually fairly easy, right? You just multiply it. So here, you have some message, multiply it by a cos, and then you just get the output. So from this block diagram, it's pretty easy to um, just draw what we had. So this is a pretty big deal, and it also serves as like the basis for single sideband modulation, which I'll talk about next, right? Does anyone have any questions about this? All right, cool. So yeah, basically a bunch of quadrature stuff. Um, so now what we need to talk about is single sideband modulation, right? So the main problem with ordinary modulation is, say we have some like audio signal here. Um, and it's just like this. It has complex conjugate symmetry because it's real valued. So it goes from negative or from positive bandwidth of m message to negative bandwidth of m. So the bandwidth of this audio signal, it's just BM, right? Because we only kind of count the positive components, right? If we do DSP or something, so say we try to modulate this just with a cos, what we end up with is, remember, the cosine will um, multiplying this by a cosine will cause a copy to appear at positive FC and one at negative FC. So the main problem here is just that every one of these two copies has both the positive and negative bits from it. So this here is FC, and this here is negative FC, right? Now this bandwidth though, it's 2 times BM. So this is kind of terrible, right? We had a nice low bandwidth message when it was just recorded, like maybe, I don't know, bandwidth of like 4 kilohertz or something like that. And then we put it on a radio and all of a sudden it's taking twice that much. It's taking 8 kilohertz, right? So that's really annoying, especially since we don't need all of this information. We know from like the first lecture that since this is real valued, if you have this positive part here, you know exactly what this negative part will be. It has to have complex conjugate symmetry, right? So the magnitude of the negative will be the same as the magnitude as of the positive, and the angle of the negative frequency components will be negative the angle of the positive ones. So it's just a waste of resources, really, to just multiply something in like an audio signal by your carrier wave because it just doubles the bandwidth that we need. So the whole point of single sideband is to avoid doing that, right? So what we want is, so this is like a 4 kilohertz bandwidth, something like that. We would really like for the radio to actually have a 4 kilohertz bandwidth instead of an 8 kilohertz bandwidth. So this whole thing is just a method to do that. Um, so what we end up doing is a big ol' it's kind of a mess, right? But let me just see where it shows clearly what we're doing. Okay, right here. So here's what we do. We just use quadrature, right? So just like we discussed just a few minutes ago, we can actually feed two totally different signals onto the same bandwidth if we multiply one by a cos and the other one by a sine, right? But there's this special transform of data that we can take, the Hilbert transform. And when we feed it in as the quadrature input, it's going to end up totally canceling out half of the frequency domain, right? So this is upper sideband, right? So here's what we end up with. So let's say message, DSB, upper and lower. So our message, oh, let me change color quick. Our message is just going to be some kind of triangle thing up to FM. If we do DSB, and modulate this, we get what we were just looking at now, basically a triangle at the top and a triangle at the bottom, and um, they'll both have twice the bandwidth of this one. So this one here is just say like 4. This here is twice that, right? So that'll be like 8, right? What we do with upper sideband though is we literally rip our message signal in half and we only move the upper half up and we move the lower half down like this, right? So now it's all great. We started off with a 4 kilohertz bandwidth signal, and we're still modulating it even on our radio. It's only taking up 4 kilohertz, right? Four. Now the difference with this versus lower sideband, it's just you see an upper sideband, we are taking this positive half and moving it up, taking the negative half and moving it down, right? When we do lower sideband, we actually take this negative half and we move it up, basically, right? So what we would end up with is like this here and like that there. All right, so yeah, that's basically the this here is then DSB. This here is upper sideband, and this is lower sideband. All right, so this is like the good kind of AM radio because we're not being wasteful. We're not using twice as much bandwidth as we need to be using. We're being efficient with power. This is like kind of the way that it's meant to be, but it's just complicated. First of all, we need to use quadrature, so we have to modulate one of our message by a cos, then we have to multiply this weird distortion of our message by a sine, right? And the real question is just about this weird distortion of the message. So this is where people end up getting super um, confused on the exam. If you guys haven't been coming to class, you'll actually end up seeing this integral. You end up trying to solve this integral. It'll be a disaster. You're really not meant to solve this integral. So let me just kind of show you what it ends up looking like. So here's lecture slide 6 or lecture set 6. Um, so it's talking about these initial concerns about lower sideband, upper sideband, dual sideband. So the real thing that we're trying to do here is figure out a good way to cancel out all the lower frequencies while leaving all the ordinary frequencies. So this goes through all the details of that. The main thing is that in frequency domain, we just have this signum function, and it multiplies everything positive by 1 and everything negative by -1. So it's kind of what we do as the base here. So the Hilbert transform is this basically. We take our input signal, x of t, or our message, and we take the convolution of that with 1 over pi t, right? So the nice thing, this is awful, obviously, in time domain. This isn't like a convolution that you're really expected to be able to do. But you see, in frequency domain, it's easy. To take the Hilbert transform of a signal in frequency domain, just multiply it by -j times the signum function. So all of the positive frequencies multiply by -j, and all of the negative frequency stuff just multiply by +j, right? So it's actually super easy to do. The integral form is pretty scary though. So let me see if it's written here somewhere. Often Daniel does like to write this on the exam and it tends to throw people off. So yeah, I'll just write it somewhere here. Okay, cool. So basically here, this x hat of t, this will be the integral from negative infinity to infinity of x of tau times 1 over pi of t minus tau, and the integral is taken over tau. All right. So this is like it's a pretty messy integral, right? Like say x is like a cosine or something. No, I don't think anyone in the class can actually do this kind of integral, but you're never really meant to. Just always solve it frequency domain, right? It's easy as long as you have the frequency domain representation of your signal x, then you can just get the Hilbert transform of it. Just like I said, multiply everything in the positive frequencies by -j, everything in the negative frequencies by +j, and then everything else works out. All right. All right. Are there any questions about that? That's pretty heavy stuff, but yeah, most of these problems you can just solve graphically, really. So the biggest thing, usually for these single sideband questions, it's just asking you to graph things. So it'll be something like what you saw in the assignments, right? So say you have this message signal, and then it'll just be like draw the upper sideband modulated signal if FC is equal to like 2 megahertz or something. So you just take that and you just draw it, right? Just keep in mind the ratios. So whenever you're drawing charts or graphs or whatever, make sure you've labeled the axes nicely. So when you do a single sideband modulation, the amplitude just gets multiplied by 1/2, right? So you rip it apart, you move negative down, positive up for upper sideband, and just multiply both by 1/2. So most of this stuff you can literally just do graphically like that. So don't go trying to write a whole bunch of equations unless it's asking you for it. Don't ever try to solve the Hilbert transform in time domain. You're not going to get very much done in the 100-minute long exam, right? So yeah, there
I have a
is a.
question.
Oh yeah, yeah. Go ahead.
Yeah. So you said it's the magnitude is 1/2, but in the equation, why is it saying a quarter for the upper side band? Like the formula is just here.
Um, that is because these are the what are they called? The positive and negative pre-envelopes or positive or negative analytic signals. They get multiplied by 2, right?
Yeah.
So I think back over here, I think yeah, the pre-envelopes. So if we look back at these slides here, oh yeah, right here. So you see, taking the pre-envelope already multiplies it by 2. So then you multiply it by 1/4, and the result is 1/2, right?
Oh, okay. Yeah. I see. So this
Yeah.
is after taking the pre-envelopes. Then we use the single side band. Then we
Oh
calculate.
yeah, yeah, for sure. So if you're going to use those equations that were shown on this slide, right, you need to have the actual pre-envelope equations, right? But if you're just gonna kind of like naively chop m in half, right, then just divide it by 2. But if you're gonna properly take it with the pre-analytic signals and everything, then
Yeah.
just recall these are multiplied by 2 initially, so you need to
Okay.
divide
I
by
see.
4. Yeah.
Yeah. Okay. Makes sense. Yeah.
Oh,
Thank you.
yeah, no worry. Okay, cool. So yeah, basically in all of these cases for DSB, for both SSBs, you demodulate them in exactly the same way, right? So say we have, uh, let me just undo that. I'll use blue as the background. So yeah, say we have this modulated signal here, and we want to demodulate it. Um, so what we do is we just multiply it by the cosine at FC, right? So whenever we multiply something by a cosine, remember cosine has impulse at both positive FC and negative FC. So that means we get 2 copies of whatever we're multiplying it by. One gets shifted up by FC and one gets shifted down by FC. So say with this one here, we're going to get 1 copy shifted down by FC and 1 copy shifted up by FC. So we can just draw that. So we'll get 1 copy of this at 2FC now because it was initially at FC and we moved it up. And then we get 1 copy of it down at 0, right? And likewise here, we're going to get 2 copies of this negative frequency signal. One's going to get shifted up and one will get shifted down. So we end up with one here, and then we end up with this one here, right? We multiplied them by coses, so they'll all have 1/2 the initial amplitude. So these all have 1/2, so the amplitude will now be 1/4 here, right? So this is always how we're going to demodulate SSB and DSB. You just multiply it by exactly the correct sinusoid. So, and then what we do is we feed this through a low pass filter, right? So say maybe this would be the filter. right? And then that gets rid of these ones that we moved way up to 2 times the carrier frequency. So yeah, this is the general approach to demodulating all coherent AM signals. So whether you're using DSB or you're using SSB to demodulate it, just multiply it by exactly the correct carrier with the right phase, and then filter out all the high frequency stuff, and you're left with this perfect reconstruction of the message signal, right? So this is just for coherent. If you have that original AM where you have the one plus thing, you can just demodulate it with envelope detector by like hopping from peak to peak, right? But for all of this other stuff, you have to do coherent demodulation by multiplying by exactly the correct sign sinusoid. Let's see if there's anything to talk about that. Don't think so. Oh yeah, so coherent detection, basically, this just talks about like if you have a little bit of phase error in your demodulating carrier, you end up just demodulating less of the carrier. And if there's something else modulated on the opposite carrier, like in quadrature, you start mixing those together. So that's kind of just similar to what we were looking at with these here. These are really the key here. So any kind of mismatch between your alpha and beta with a phase, it's going to turn one of these no longer into one, and the right, and the other one will kind of turn into not zero, right? So as um, alpha and beta here become um, different due to some phase shift, this gets smaller than one and this gets bigger than zero. So yeah, any kind of phase error between your modulating carrier and your demodulating carrier, it's gonna either, in the best case, just attenuate your signal a bit. In the worst case, it's actually going to mix in some undesired signal from the other quadrature channel, right? Uh, cool. Are there any questions about that stuff then? I think that's actually all of AM. I don't think there's much else to talk to about AM, except just maybe keep in mind if you're expected to, is this the Costas receiver one? Maybe it was over here. Oh yeah, right here. Yeah, as to actually how you get that phase lock, that perfect carrier, just usually doesn't cover it on the exam, but you can use a phase lock loop. And the special kind of phase lock loop that we covered at the start of the term is this Costas receiver. It's a bit awkward because it's a much more complicated phase lock loop than what we're covering now for FMD modulation. And we just barely talked about it. But if you're asked how to generate like a coherent carrier, you can just have these slides prepared. And you can just say Costas loop, maybe copy down some equations. It's all discussed here, right? But basically, if we have some DSB radio signal coming in, this is going to perfectly lock so that the voltage controlled oscillator ends up being just the perfect carrier for us to demodulate, right? So it's just kind of what we use for that. All right. Any questions about FM? Or I'm sorry, about AM? Any questions about AM? That's all of AM. Oh, sorry. I've been missing a whole bunch of these questions here that haven't been. Uh, let me go back. Natha, do we have to multiply by 2 cos to get the amplitude back when demodulating? I mean, not really. You just amplify it at any point, right? So Jag, you'd ask about the demodulation of quadrature. Yeah, it's the same as any other demodulation. It's just you demodulate the one signal with the ordinary cos and you demodulate the other signal with a sine instead, and everything will just work out perfectly, right? As long as your phases are locked mm, on the carriers, then demodulating quadrature, it's no different from demodulating DSB or single sideband. It's just rather than just demodulating with the cos, he'll demodulate with both the sine and the cos. Yeah. Okay, cool. Then Kinez, you're direct messaging me so other people can't see what you're writing. What if you bring the textbook but remove some pages to make it under 600? Is that allowed? I don't know, man. I think it's probably allowed. Okay.
I have a question.
Oh, yep, cool.
So for the single sideband you were talking about, like when we want to demodulate it, so we can just time the frequency of it and then the close frequency of it, so we
Yep.
can and go through a low pass filter. So if we are at the negative FC, so we just times by cos negative FC, and then go through a low pass filter, or just cos of FC.
Oh, I'm sorry. Could you just repeat the second half of your question? I kind of didn't get it there.
Oh yeah, so when we
We
want
have
to demodulate
this.
it, if
Yeah.
the signal or whatever it's at the negative FC, do we times it by cos of negative FC or just
Oh,
cos of
no,
FC,
but cos of negative FC is the same as cos of positive
right?
FC.
It's the same thing,
It's
right?
the same thing. So no matter what, cos of FC already has frequency components at positive and negative FC, right? So I think maybe what you're asking is, do we multiply not by cos negative FC, but by e to the negative jfc, right? And yeah, we basically do, but we can't really multiply actual signals by these complex waves like e to the j whatever. So we always just multiply them by the cos. So the cos is always going to do both the positive and the negative. It's
Okay.
gonna, yeah.
Mm,
So that's why we end up with this shifting up and this shifting down, and this shifting both up and this
okay.
shifting down. There are ways to actually just move it up or down, but you need two wires for it because it's in complex domain. Yeah.
Yeah. So basically we just multiply by cos of the
Yeah.
frequency.
And then
Okay.
just always filter out the thing that you don't want. Yeah.
Yeah. Yeah. Thank you.
Okay, there's another question here. Oh, direct message again. How close is the 2023 exam example to the actual exam? I don't know. I have no idea. Sorry. Oh, so yeah, he only wrote the new exam the other day and I haven't seen it. I have no idea what it's going to be. All right, cool. So yeah, that is AM. Then I had, let's look back maybe at my list here. Okay, so we covered coherent, non-coherent, single sideband, quadrature, all the kinds of AM and signal distinction. So it's great. Oh, super heterodyne. All right. So yeah, I guess we're talking about super heterodyne now. So yeah, we've already covered a little bit of the really important stuff, just talking about single sideband, dual sideband. Super heterodyne is an interesting concept because it's super similar to amplitude modulation, but also not really. The entire point is different. So with super heterodyne, all we're doing is moving radio stations around, right? So say like in real life, you have a radio station at like 88.1 megahertz, you have another radio station at 90.1 megahertz. Like how do we move the 90.1 megahertz one down to like 88.1, basically? How do you change the carrier frequency of something? So that's all what this super heterodyne is about. There's almost always a question on the exam about it. So yeah, I would super strongly suggest that you cover it. So in your review. So let's just see. All right. Oh, I think I didn't even open the super heterodyne slides. Hold on. All right. So yeah, frequency translation and a super heterodyne receiver. All right. So this is basically kind of the situation we have. So what do we have here? So yeah, I guess we can actually go through and do this example even. So here we have this signal here, a radio signal, and it's just at F1, right? So what does it look like if we multiply it by a cos? Well, that's the same thing as if we were just going to do demodulation, right? Except this could be just different. So say if we're multiplying it by some FLO and FLO is bigger than F1, right? What that means is we're going to get two copies of this thing. One's going to be move all the way down to really far. It says FLO is bigger than F1, so it's going to move all the way to negative frequencies. And one's going to move way up here to F1 plus FLO, right? And we get exactly the same doublet for this negative one, right? So basically we can do this. We'll have this guy here and also this guy way up here, right? So that's from moving just the positive F1, right? And then we have this one here and this one way down here. So that's from moving the negative F1, right? So this is just the same as when we were doing amplitude modulation. When you multiply something by a cos, you're just going to be shifting everything there, both up and down, right? And then this next one is asking, what if FLO is smaller? So if it's smaller, then we'll just be moving the F1 to both positive and negative frequencies, basically, something like this. Right, so here this will just end up moving down a little bit and also moving up a little bit, two copies, and we get the same thing in negative. So as you can see, we just moved our radio station to a totally different frequency, right? So first we were at F1, and now here we are at F1 minus FLO. And LO is our local oscillator. That basically means we can decide what it is, right? So we can kind of tune where we want this guy to be, our F1 signal. After we multiply it, it won't be at F1 anymore. It's going to be at F1 minus LO, FLO in this case, right? And then like what we were doing with demodulation, usually you're just going to filter out the copy that you don't want, right? So the F1 that got moved way up to F1 plus FLO, generally we just get rid of it, right? So you see, this is how we actually moved a radio station that was at F1 to this other negative frequency, F1 minus FLO, right? So this is the real fundamental basis of all this super heterodyne stuff. The reason is your radio doesn't actually demodulate everything. It only demodulates a single radio station at 10.7 megahertz, right? And all the actual radio stations are way up here, between like 88 and 108. So what your actual radio, like FM radio, is always going to do is it's going to pick one of these radio stations and it's going to move it all the way down to 10.7, or maybe it'll move it all the way down to negative 10.7, right? It could do either. One of them is called high side tuning, and the other one is called low side tuning, right? And you can always choose which one you want to use, right? So this is the real basis of super heterodyne. We're just taking a radio station that we have and moving it into the radio channel that we want it to be in by multiplying it by some frequency, and that frequency is called FLO, right? So the real trickiness happens when, um, let's see, we just end up with this terrible problem of the image, right? So you see, we can move our desired radio station to either negative 10.7 or positive 10.7, right? So let's say the radio station we want is right here, and we have a whole bunch of radio stations. Okay, so let's say this is the one that we want. Okay, and we're going to move it to negative 10.7. So we do FLO equals to our radio station that we have. This is FRF. plus 10.7. So when we multiply our whole radio spectrum, everything coming off the antenna by FLO equals FRF plus 10.7, the result is we're going to end up moving the radio station we want to negative 10.7, right? The main problem though is we're also going to be moving something else that we don't want to positive 10.7, right? Because we just multiplied this entire antenna signal by our FLO. So you see, now we have this weird radio station up here, and we've moved it into our filter bandwidth. Remember, our filter, because it's like a real filter, it's going to let through everything around 10.7 and everything around negative 10.7. So what we ended up with is we're actually receiving two different radio stations now. One is the one that we want, FRF, and one is the one that we don't want. This is called the image, FIM. So that's the whole challenge with super heterodyne. We want to move um, our desired radio station to the frequency where we want it to be, either the positive or negative frequency, right? The problem is that means we're going to be moving something else to the negative or positive frequency, whichever one we didn't pick, right? And that's called the image frequency here, right? So there's no way around that. If you want your radio to work, you need to filter out this radio frequency, or I mean this whole undesired radio station before you multiply it by the cosine, right? And that's actually the only radio station that'll cause a problem. You just need to filter out that one, okay? And then super heterodyne is always fine. So just remember, you can always move around your radio stations, move one to another spot or whatever, move what frequency it's at, as long as you take care of this image frequency first, right? So that is basically the entire concept here, right? So let's just see if there's any interesting examples. There's some more discussion of this image frequency. Yes, Mohammed, it will be recorded and posted. Yeah. So the main thing here is, yeah, it's all these different equations, but you can really just figure it out graphically, right? So if you're doing high side tuning, uh, then you set your FLO to the sum of the RF frequency that you have and the desired frequency that you want. So this is going to move our RF frequency all the way to the negative desired intermediate frequency, right? And then it's just asking what is the frequency of the image signal. And then you can just figure it out graphically, right? It's just going to be whatever gets moved to the opposite of F2, like negative F2 if you were moving to positive, or positive F2 if you were moving to negative. So you can figure these things out graphically, right? But yeah, these slides, probably good to just print them out and add them to your formula sheet because they might save you a little bit of time. But yeah, this is normal. It's just, and as you can see here, before you mix, before you're moving the frequencies around, you need this filter just to get rid of that image frequency because the image frequency is the worst thing. It's the only thing that's really going to mess up your ability to shift radio stations around, right? So you always have to get rid of just this one radio station before you mix by your local oscillator, right? So yeah, that's usually a kind of cheap filter. It's just called a pre-select filter, right? Um, I don't think there's too much more, but yeah, so here's the whole thing, right? So right here, this is just the radio demodulator that just works at the 10.7, and everything beforehand in the radio, the RF selection, the RF section, and the mixer, that's just to move your desired radio station to this FIF, this 10.7, right? So yeah, you guys had questions on that on the assignments, and I think you all did pretty well, so I think it should be fairly decent. Are there any questions on super heterodyne? Make sure you guys, like tomorrow or even Friday, whatever, just practice a little bit these calculations, some super heterodyne problems, because they're honestly so easy and so fast if you're well rehearsed and practiced with them. They you'll be able to solve basically any problem you have in like 5 minutes. Whereas if you have to stumble, if you have to think about it a bunch, it could end up taking you 20 minutes and you don't have that much time on this exam, right? So just the concept makes perfect sense, but make sure that you're quick implementing it, right? All right, cool. Let's go back to my big list. All right, so we did super heterodyne. Now we are on to my least favorite topic in the course. It is complex envelope. Complex numbers in general are pretty tricky, right? Let's go over to the notes for it. All right, so we have this slide deck 8. This is called bandpass signals in complex envelope. So I'll just discuss quickly the intention that we have here. So you see right here, we have some kind of a modulated message, and the main annoyance is just that it's already at the carrier frequency, but there's nothing really special about one carrier frequency versus another, right? Ideally, we'd like to be able to analyze a signal without really caring about the carrier frequency at all, right? So one thing that we can kind of do is just, well, it's the whole topic here. We just take the complex envelope. So what we do is first, you see, this is a real signal, real valued signal. So that means it has conjugate symmetry, right? The there's a mirror image in the positive and negative frequencies, right? The first thing that we want to do though is get rid of that mirror image. So we take the positive analytic signal of it using the Hilbert transform. We get rid of this negative component. So now all we have is this positive component here, right? That means it's no longer real valued. It's complex numbers, but it's not that big of a deal. Then all we do is just shift it to the left by the carrier frequency, right? So now rather than having this whole shape with the positive and negative copies and everything when we're analyzing the signal, now all we have is this, just one little shape right at the origin, and you see there's no factor of FC anywhere. So the whole point of this is we want to do math on this and not care about the carrier frequency because we can just set the carrier frequency to whatever we want. We shouldn't have to worry about it, right? So here is, yeah, that's the main thing. So just get rid of the negative component using the Hilbert transform, and then shift everything to the left by multiplying it by e to the negative j 2 pi fct, right? So what that is basically doing is, you see this equation here, this is the general form for what is shown in this graph, right? Um, Basically, if you have some xi and xq message signals and you multiply them by this cos and this sine at the carrier frequency, you just get this pattern, right? But you actually don't care about this cos and this sine. All you really need to care about are these two message signals, right? So those two are the real component and the imaginary component of the complex envelope, right? So basically the complex envelope is just everything important about the signal once we ignore the carrier frequency, right? So yeah, there's lots of different ways of showing this stuff. Oh yeah, so usually it's kind of defined backwards, right? So the complex envelope is anything for which this is true. So this here, the x tilde is the complex envelope, right? So what it's saying is first move it to the right by FC, right? When we multiply something by e to the j 2 pi FCT, it'll just move to the right by FC and then take the real value of it. So say we start off with our complex envelope, our x tilde, and it's just this, right? Then we move it to the right. Ah, move it to the right by multiplying it by e to the j 2 pi fc. So now we have this. right? And then we take the real value of that, and that causes the conjugate symmetry to appear. And it means now we get basically positive and negative frequencies, just like that, right? So this is defined backwards. This is kind of how to get our bandpass signal from the complex envelope, but it's also the actual way that the complex envelope is defined as well. So it's exactly the steps we talked about, but in reverse. So in reverse, right, you just get rid of the negative thing, and then you shift what's left to the origin, right? And then, yeah, that's basically all there is to it. So we end up using this a lot in the angle modulation sections, the FM stuff, right? And then, oh yeah, so you can see here's the whole procedure. Just get rid of this, and then move what's left over, right? So right. This UP here is the positive pre-analytic signal you just get from adding the Hilbert transform to the original function, right? And then you shift it to the left by multiplying it by e to the negative j2 pi fct, right? So yeah, a lot of complex numbers. It's kind of heavy, but it's very straightforward once you figure it all out. So yeah, basically, once you have that complex envelope, remember it's not real valued because there's no conjugate symmetry. It might be, but it would be a bit of a coincidence, right? So what we end up with is it has real and imaginary components, right? And the real component is just this xi of t that you could feed into kind of a quadrature multiplier or a quadrature modulator. And then the imaginary component is just this xq of t, right? So basically you can kind of think of the complex envelope as whatever you would need to feed into a quadrature modulator, those two message signals to get the same output, right? Um, then envelope and phase. So this ends up being a bit weird. What we end up going into in the rest of this content is about how to do like signals and systems analysis, basically transfer functions with when we're dealing with things in the uh, complex envelope domain. So so remember, like normally you just have this, right? You have a bandpass signal going in to some filter H, and then just Y comes out, right? When you want to figure out what complex envelope you get coming out of the complex envelope going in with the complex envelope of the filter, it just there's just some math details. Your result ends up being double what you need it to be, right? So you can do all the math just normally, but then the output, just divide it by two because what you get, not the complex envelope of the output, you get twice the complex envelope of the output if you try to do just ordinary linear systems analysis with complex envelopes. So yeah, just remember that. It's not that big of a deal. It's just whatever you get as the output after doing the convolution to figure out your um, output, just divide it by two, right? I think, yeah, that is about it. So, um, in angle modulation, it's so easy, really. So remember the big thing about the complex envelope is just that basically the frequency terms should disappear, or the carrier frequency terms should disappear. So remember when we were dealing with these signals like this, right? So this is like an AM signal, right? Um, just cross it out. So just cross out the cos, and then for the sine, just replace it with like a J, and then you basically get your complex envelope just like that, right? For frequency modulated stuff, it is almost easier. So here you want the complex envelope, cross out this term here that has the FC in it, and then turn the cos into a E to the J. All right. So that's it. You'll almost surely have to do this a few times, but yeah, so the actual like S tilde here is just equal to AC times exponent of J times phi. right? So it's super easy taking the complex envelope most of the time. Just get rid of everything that has like a carrier frequency in it. And then sometimes you need to turn real things into complex things. So just replace this cos with the e to the j, right? No, Alidad, it's just phi because there's no 2 there, right? The 2 is just in the carrier frequency term. It's not multiplied by the phase term here. So no, it would just be the exponent of j times phi, I think. Yeah, what's happening? Okay, cool, cool. Um, all right, cool. So yeah, that is angle modulation. That is a painful topic. Hopefully things go well with that. So now let's move on. I'll go back to this list that I had. Okay, good. We have almost an hour left. So yeah, we've covered everything up to um, section 5. So section 5, this is a pretty big deal. We have a lot to talk about here. Um, so what we have, oh yeah, I wanted to talk about bandwidth. So remember previously, up until now, we've always just been putting the information on the radio waves by changing the amplitude of the carrier, right? That's just a terrible way of doing things, honestly. It's so terrible to encode information on the amplitude of something unless it's like a relative amplitude. It's just so noisy and the quality is always so terrible. So back in the they figured that if they would actually just encode the information on the frequency of a wave, it's so immune to noise. It's really, really just so much better in every way. It just takes more bandwidth, but it's not really that big of a deal. So this is a completely different concept, right? So now rather than changing the amplitude of a wave, we're just going to leave the amplitude constant. That way, say if like atmospheric conditions change how much the wave is like attenuated or something. We don't care because all we need to keep track is the frequency. So that's the whole point between this angle modulation. So that's phase modulation and frequency modulation. So just a few things to talk about with it. I'll talk about the kind of narrow band way of making it with Armstrong generators. Who knows? Maybe Daniel wrote a question on the exam about that. We don't know. Bandwidth is a tricky concept with FM. It really is, especially for the people who haven't been attending class. If Friday is the first time you've seen a Bessel function, like you're not going to have a good time, right? So they're easy questions once you've kind of gotten the hang of them, right? Discriminator, this is a terrible, terrible topic. It gets super confusing, and there's almost always a question on the exam about it. And then PLL, normally Daniel doesn't cover them in detail, but he actually promised you guys that there's going to be a question on PLLs on this exam. So we'll talk about it. All right, so let's go back over to our slides. Angle modulation. All right, so yeah, here is the form of modulated signals. So remember in amplitude modulation, our information is on the amplitude itself. So in ordinary AM or a DSBFC, we have it in this weird kind of 1 plus KA times the message form. Then in ordinary DSB and in SSB, we kind of have these weird situations here, but we're just basically making the amplitude proportional to the message frequency. See, in angle modulation, we always keep the amplitude of the wave constant. We just change the phase, right? So here is our basic prototype for both phase modulation and amplitude modulation. You see, we have this cosine and it's just chugging away. So if we were doing nothing, it would just be going at carrier frequency FC. But we're also not just changing its phase based on its carrier frequency. We're also going to be changing its phase a little bit based on our information, right? So you can see the phase is everything within here, right? So the instantaneous phase at a time, it's really just going to be how many carrier cycles we've gone through plus how much phase we're adding. We take the derivative of that to get the instantaneous frequency, and we see the frequency is always going to be around FC, but we're also going to be adding this little change, deviation to the frequency based on the slope of our phi of t, right? So all of the main parameters, it's really just about how we kind of change this. So how much are we going to change the frequency for a particular amount of message signal? It's all just concerns like that, right? So we have two different types of angle modulation. We have phase modulation. Do you see that's where we're literally just making the phase proportional to our message. So we just multiply our message by some KP, the phase sensitivity factor, and we just send that down the line. So with that, anytime our message is static and quiet and not changing, even if it's high or low, we're just going to be transmitting a carrier, right? Anytime our message is kind of changing, um, the phase will be changing with respect to time, so that'll cause a little bit of frequency deviation, right? So yeah, basically that's all of that. You see, with frequency modulation, we're not going to be putting the information directly on the phase. We're actually going to be putting it on an instantaneous change in the frequency. So this is what we end up with, right? So see previously with phase modulation, this whole ugly term on the right here was actually just Kp times m of t. Now it's not because we don't want the phase to change instantaneously when we change the message. We want it to change gradually. So we're going to basically integrate our message so that the amount of phase we're adding to this cosine overall is per unit time is proportional to our message. So in the end, this ends up, say if the message is 1 volt, it's going to increase our carrier frequency by kf hertz, right? And when it goes back to zero, then the cosine frequency will go back to FC, right? And if m of t is -1, then basically it's going to keep subtracting kf radians per second or kf hertz per second, I suppose. Um, so then the actual transmitted frequency would be like FC minus KF if the message is -1, right? So when we're using FM, we never change the phase instantaneously or abruptly like we do with phase modulation. We change the frequency instantaneously and abruptly, right? So that's why we have to integrate here. So yeah, lots of interesting things. It's just it uses way more bandwidth, but the noise is so much better. And we study that at the end of the class. So, or I mean at the end of the term. So yeah, here's our what it just looks like, right? So we just have our carrier wave. And then with FM, you see when this message is high, it means the frequency is high. And when this message is low, it means the frequency is really low, right? Whereas when with phase modulation, you see when the slope of our message is really pointing down, that causes the frequency of our carrier to be really small. And when the slope of the message is really pointing up steeply, that causes the frequency of our carrier to be super high, right? So yeah, these are identical in every single way, except for what we consider the message. You see? So here, phase modulation, it's just the phase as a message. Here, frequency modulation, the phase is the integral of the message, right? So yeah, make sure you have these written down. A huge part of solving these problems here is just pattern matching, right? So say if there's if you're just given some kind of equation and it's just going to be asking you, okay, what's the frequency deviation or the frequency sensitivity or the peak frequency deviation? You just need to figure it out from all of these equations, right? So it's pretty straightforward though. Um, Oh yeah, and then you can see here, you can use a PM radio, like a phase modulation radio, as an FM radio if you want, right? So say you have like a phase modulator, just integrate your message first, send it through a capacitor, and then transmit it, and then the output will be like an FM radio, right? Say you have a FM radio, you want to use it as a PM radio, just take the derivative of your message first, then feed it into the FM radio, and the output will be like a PM radio, right? So they're really just identical things. It's just about what you consider your message, right? Um, Okay, so then we end up talking a whole bunch about bandwidth. Um, so there's this one particular case. If we set the phase or the frequency deviation super low, so we make it so that, say, for a 1 volt increase in your message, we'll only change the frequency by like a few hertz or something. If you make it really small, we end up with this case called narrowband FM, and it approximately looks almost like amplitude modulation, right? So it's just a kind of weird case. And in fact, rather than use a proper radio and everything, you can literally use an amplitude modulation radio to make this kind of narrowband FM. You see, all you need to do is add a pure carrier tone, just this cosine, as well as a DSB signal modulated with a sine instead of a cos. And if you add those two together, you actually make a narrowband FM signal, right? So this is just one of the easier ways of making FM, and it's good because you can kind of do it cheaply and with a super reliable carrier frequency. So yeah, that's kind of just so here on this slide, it shows you the details. So you probably want to print this out because there might be an narrowband FM question on the exam, right? So usually this isn't such an important thing, but like walkie-talkies use them. And then there's that one tutorial that we had a few weeks ago where Daniel talked about Armstrong generation. That's where you start off with narrowband FM and you kind of just keep squaring it. You're taking like yeah, you just keep squaring it and it turns into wideband FM in the end, right? So it's indirect FM generation. You can generate a nice wideband FM signal from a narrowband just by squaring it basically a whole bunch of times, right? All right, so that is the narrowband stuff. For wideband, it gets a bit trickier. So we saw with narrowband, the bandwidth was basically the same as the bandwidth for DSB. So say if we have like a 4 kilohertz bandwidth radio signal. Oh, let me see where that drawing was. Uh, yeah, so basically if we have like a 4 kilohertz bandwidth radio signal, here we just get the same as what we got with DSB because this is DSB. So basically we'll have a bandwidth of twice what our audio signal was, right? Or our message signal here. Just because it basically is DSB, right? In general, though, that's only because for narrowband, our frequency deviation is super low. Most of the time, FM is going to take way more bandwidth than just twice our message bandwidth, right? So how much bandwidth it takes is a pretty tricky problem. So here, in this slide deck, this is slide deck 10. You guys will need a few equations out of this if you're still making your formula sheet. So just kind of keep that in mind, what's important to write down here. So for a single tone, we can solve kind of analytically what the wideband FM bandwidth will be. And it's a mess. It uses these Bessel functions. It's only important for this course, to be honest. Single tone FM just isn't that big of a deal in real life, but whatever. It's just math that we can do, so they make you do it. And then we have our little Carson's rule, which is pretty easy. So basically what we're doing here is first, we start off with a single tone FM. Okay, so what we're doing is the FM form, and for the message, we're plugging in just a cosine, right? So then we take the integral because when we're doing FM, we have to integrate the message, right? So we end up with this. So we have a cosine of this carrier term plus our message term, right? Then what we do is take the complex envelope, right? So remember what we do for that? We just covered it. You cross out the FC term and you turn this into a complex exponential, e to the j, right? So once we have that complex envelope, we see it is in fact periodic, right? Because it's just going to be e to the j of beta sine. So it's a periodic function of a periodic function. It's going to be periodic, right? So it's pretty ugly though. I don't know. It seems to not actually be written here, but the main thing here is that since we have the periodic function, we can try to take a Fourier series of it. All right. So this is the tricky thing. No one's going to succeed in taking this Fourier series because the integral gets too hard. But that's okay because somebody figured out what to do with this integral like 300 years ago, right? So here is what we are trying to do. So we have single tone FM. We've taken the complex envelope of it. So it looks like this, right? We just by crossing out the carrier term and then turning the cos into an e to the j. And now we're trying to take the Fourier series of it. So to take a Fourier series, we need to take the inner product integral of this with a whole bunch of different frequencies that are all harmonics of the fundamental, right? Here. So our representation will just be a big sum of these different sinusoids multiplied by their weights, and then their weights are going to be given by this integral, right? So we haven't done anything crazy yet, but we've already ended up with this crazy form. So you look at this, no one in this class can integrate this. It's so hard. It's not possible to integrate, and you're not meant to integrate it. This is just one of those special kind of integrals that some they figured out years ago. Actually, for heat flow, it was initially, I think, but yeah, I can't remember. So basically, what all we need to do is do some manipulations until it turns into this kind of nice form here. So you see here we have the integral from negative pi to pi of e to the j beta sine x minus n times whatever, right? So this is as far as we can get, right? But that's okay because that form, what we've just done, it's a super famous function just called a Bessel function. So no matter for whatever value of beta and whatever value of n, someone has gone and figured out the value of this integral, and it's just a number. It's literally just a number that you look up. So none of us ever actually has to figure out how to do this integral. It's just a number. So once we put it in this form, you just plug it into a calculator or you look it up, right? So this is the Bessel function. It's just a number. It's a function of n and beta, and it gives us the value of this integral, right? So we have the actual charts here. So say if n is equal to 0, then we have j0 of beta. And for whatever beta value you have, say we have beta equals to 5, you can just see that the value of the Bessel function j0 at 5 is like this. What is that? Negative zero point 0.2 or something like that. So yeah, you just never have to worry about this integral. You just need to show that that Fourier series that we were trying to take results in this integral form, and then you just look up these values on a list, right? So let's go back and remember why we're here. We took the complex envelope of our single tone FM and we saw it was this. And then we want to write it in this form of Fourier series. So now that we know that these CNs here are just Bessel functions, we can express our single tone FM, the complex envelope of it, just as a big sum of these Bessel functions multiplied by the different complex exponentials, right? So let's just look at what it looks like. It's like this. Okay, so say we just did a FM, um, single tone FM. So here's our carrier frequency, right? Our message frequency is just the spacing between these, right? And then you see their amplitudes are just given by the Bessel function. So we want to find the amplitude of this one. That is one sideband to the left of our carrier. So that's going to be J negative 1. And then we always put in the beta value. And the beta is kind of our how much we're modulating it from. So that's kind of just a equation that you need for this. So yeah, as you can see, when we actually try to look at the spectrum of an FM modulated signal, we just get an infinite number of all these different impulses. So FM always technically has infinite bandwidth, but in this course, we just consider the bandwidth only significant up until the one Bessel, like up until the Bessel functions are all less than 0.01, right? So that's what it says here. So to find the actual bandwidth of an FM signal, you just figure out the beta of that signal. That's like the modulation depth. And then look up on a table or the chart all of the different Bessel functions of different orders up until the order at which they're all for that beta going to be less than 0.01. And then that gives you your N max, how many how many Bessel functions left and right you have to go. Multiply that by your message frequency and then times 2 because it goes to the right and left, and that's your bandwidth, right? So yeah, it's kind of a lot of nonsense. I mean, single tone FM, that's not what FM is for, but whatever. It's just an excuse, I think, for you guys to use Bessel functions. It's not super important, but it's not worth being scared of either. It's just we're able to analytically find the bandwidth of single tone FM using this crazy mathematics, right? So yeah, that is about it. Are there any questions about single tone FM bandwidth and Bessel functions? All right, cool. Yeah, I've discussed this stuff with quite a few of you in class and after class and whatnot. So I think mostly you have a good understanding of it. So remember, that's only when you have a single tone, right? Um, if you have some arbitrary message, you can't use the Bessel functions or whatever, because remember, we got to the Bessel functions by imagining our message was just a single tone. If you have just a general FM message, um, I mean, the correct way to find the bandwidth is just to simulate it and you measure it. But for this course, all we do is Carson's rule. So you just say the bandwidth is going to be approximately 2 times the sum of the message bandwidth plus the frequency deviation, right? So that beta value that we were looking at before for the Bessel functions, that is how much our FM signal is going to change at most divided by um, the actual message frequency, right? For this, we just care about the actual deviation. So say if when our message is +1, our carrier frequency goes up by like 1 hertz. And when it's -1, it goes down by -1 hertz, and it just the message is between -1 and 1, then this would just be 1 hertz. It's how much our frequency is deviating based on our input message signal, right? So you see with narrowband FM, the frequency deviation is super small, so it's approximately 0. So we just get twice the message bandwidth. And that's kind of what we were looking at with the narrowband FM. As our beta value gets bigger and bigger, remember our FM starts getting like crazier and crazier, right? So, oh, this is wrong to look at here. So you can see for very small frequency deviation, the bandwidth is pretty small. It's all just clustered, right? And as we get a bigger and bigger beta, you see more and more of these impulses, more and more of these sidebands get more and more significant. So it's not so much about the message bandwidth anymore as much as about the frequency deviation that really causes the resulting bandwidth of the total signal. So that's why with this Carson's rule, um, try not to use this in real life. It's a terrible rule, but for the course, it's fine. It's just that's why you see it has both a dependence on the message bandwidth as well as on how much we're abusing the frequency modulation with frequency deviation, right? All right. Are there any questions about that? So we did Bessel bandwidth of single tone FM as well as bandwidth of general FM using Carson's rule, right? Oh, sorry. I think I missed out on some more questions in this chat here. Let's see how far behind I am. Ali Dad, can you say again how you get the range? That was for the Bessel range, I think. So yeah, basically, say we need to look at it. Uh, okay, so yeah, say that our beta value is like 4, right? So we would just look at this table and we see, okay, so at 4, how many Bessel functions do we actually care about? So how many Bessel functions here are bigger than 0.01 at beta equals 4? So we see this one, J0 is really significant, J1 is pretty like significant, and we see pretty much all of them are still significant, even this J6 is, but the J7, it's not plotted here, but it would actually be kind of like this. So basically, just from the graph, you'd be able to see you need to count up to and including the J6, right? Um, Here, though, if you actually want to find the range of the Bessel functions you need, I think you kind of just need to use this little table that was given. Oh, here. So yeah, this little table in this slide, it actually tells you how many you need to include. So if beta equals, say, 2, you need to include up to J4 and J negative 4. So you get a span of 8, right? And if it's 5, then you need to include up to positive 8, negative 8, right? So yeah, that's kind of how you get the range of the Bessel functions you need. Let me see. Hannah Abia, is the Bessel 4.2 table in the slides enough to put on the cheat sheets? I'm not sure. I hope it would be Hannah. I don't know. It looks like a bit of a brief table, but I guess it's fairly good. It's a shame there aren't a few more complete values between 2 and 5, but it's probably good enough. I would definitely put your the graph on there, maybe. But NASA, can you use Carson's rule for single tone FM? You can, but don't do it unless you're specifically asked to. You'll probably lose some marks. If you're in a time crunch, though, do it for sure. It saves a lot of time versus trying to find the bandwidth of single tone FM using Bessel, but you're probably not going to get full marks for it, right? Sandali, is it possible to do an example for Bessel function? Let's see. So we can just kind of maybe walk through this one here. I think there was a good example somewhere here. Oh, here's a good table of Bessel functions. All right, cool. So yeah, let's just say that we have an example. So say what we have, where's something that we can read this off of? Oh, so here's single tone FM. Just looking for something that actually has better values in it. Oh yeah, so that's kind of cool. So say we have a a frequency modulated wave. Let's go up to an example here. All right. So say we have this is our actual wave. So one question that comes up fairly often on the exams I find is that it'll be a bit of a trick question. It's going to be saying, okay, so you need to modulate, do FM modulation for the signal. Choose a beta value such that the third side lobes have zero power in them. All right. So say like it would have something along those lines. So like choose beta so that the third side lobe has zero power. So it's kind of confusing, but just remember all the energy in the different side lobes are determined by the Bessel function. So say J0 of beta, J1 of beta, etc. Right? So to solve this, basically you just need to find a value of beta so that J3 and J negative 3 are equal to 0. So we want J3 of beta equals 0. So for something like that, all we really need to do is scroll down to our chart, right? So let's look at our different options. So if beta equaled 1, right, you can see we can kind of draw a vertical line here. We see our main lobe, the carrier leakage, our content right at FC. It'll be around 0.75, right? Are the magnitude of our side lobes to the left and the right will be around 0.45, and our side lobes even further than that, two message frequencies to the left or right will be around zero point 0.1, and everything else is negligible, right? So if we chose beta equal 1, this is what we would end up with. We would get this one here at, let's see, 5, let's say this is 1. So this is right at 0.75. And then at one side lobe down, we got it just at about 0.45, and then one side lobe up. And then further, our third side lobe is going to be, or yeah, our second side lobe, I guess, at zero point 0.1 and negative zero point 0.1. Then everything else is kind of ignorable, right? So we could use this to find our bandwidth if we wanted. But that's not what the question was, right? Question was find a beta value for which the third side lobe is exactly 0, right? So for that, let's actually look at what our third side lobe is going to be. So you see, oh no, it's not even drawn here. J1, J2, J4. All right, let's change it to four side lobe. So say that we actually want the fourth side lobe to be 0. We can look at how the magnitude of that fourth side lobe changes as we change beta. And you see, when we actually set beta to say like 7.5, it literally goes to 0. So if we are going to plot out what this would look like then, um, let's see, we get right here, we get a carrier of about zero point 0.3, right? The side lobes to the left and right of that will be around zero point 0.2. Then for the J2, this is actually pretty big. It's actually negative zero point 0.3 about here and here. And then there's no trace, so we don't actually know what this one is. Let's just assume the J3 is somewhere like this. And then the real key that we're looking for is that this one here and this one here will be perfectly 0 because their amplitudes are given by this curve, right? And we see that's a 0 crossing. So if you set beta to be equal to 7.5, you can make sure that there's 0 energy at that frequency and that frequency, right? So that's kind of like a Bessel function example, and that's quite similar to some I've seen on exams before, right? All right, cool. So I think we should probably, let me see what else we had. Yeah, so that's that. There's two big topics we have left to discuss. We don't have too much time left. So there's the discriminator and the PLL, right? So oh yeah, I'll just quickly go on Armstrong generation. If you want a wideband signal, you guys will probably have to look at the tutorial for this. But you see what you can do is just, this isn't a frequency mixer. as much as it's like it's actually multiplying the input by itself. So you can make a narrowband FM, right? And if you just keep multiplying it by itself a whole bunch of times, basically, and filtering out the bits that you don't want, then basically it'll turn into a wideband FM. So that's probably not going. Oh, Kinez, yes, that is the exact main thing. So if you're actually like shifting things to the left and right with a mixer, you're just moving it around and the frequency deviation doesn't change. When you run it through a frequency multiplier, it moves up just as much as the frequency does. So that's how we go from, say, like this little narrowband FM with just the two tiny side lobes. We feed it through a bunch of these frequency multipliers and it moves way over, but it also becomes like a glorious big FM signal with lots of rich sidebands, right? That's because the frequency multiplier, it goes through, um, yeah, it increases the frequency deviation and the effective beta as well, right? So yeah, usually that's not on the exam, but and if it is, it's mostly just some logic tricks, right? Like in this tutorial, where am I? Oh, here. In this tutorial, it's just about trying to figure out the factors n1, n2 of the squares, as well as the LO you need to multiply it by to get some desired output frequency. I can't really teach you how to do that. It's just logic. It's just a pain, but it's just algebra, right? But just remember, you can change the frequency without changing the frequency deviation by using a mixer, just the way that we do super heterodyne. You can change both the carrier frequency and the frequency deviation by using frequency multipliers, right? Okay, so then here we have this section here on demodulation. So the easiest way to demodulate a FM wave is to turn it into an AM wave. And we can do that literally just by taking the derivative of it. You see, so here is our wave. We have all of our information just in FM. So we integrate our message and we add it to the phase of our carrier basically. So if you just do some calculus, right? Just some grade 11 stuff, you take the derivative and we end up with this. The derivative now is, see, it has this big carrier term that turned into a sine. It was a cos, but now the amplitude of that strange sine carrier now depends on our message, right? So if you take the derivative of a FM wave, it turns into an AM wave, and you can use an AM demodulator to demodulate it, right? Okay, the math here is a mess, right? So normally what you would just do is totally take the derivative. The problem is the frequency domain of a derivative is this big slope here that just goes up forever. That means it's amplifying all of your high frequency noise so much, like way too much, right? So what we do is just a practical differentiator instead. That's only going to take the derivative of a small band. So you just design a filter that looks like this. It's just flat. And then right around your carrier frequency, it just has to have some slope. Just the gain of the filter needs to change with frequency. That's all you need. And then once it does that, um, it's going to turn FM into AM, right? Because think, at the carrier frequency, it's going to just attenuate it by this much, right? If it's higher frequency, the output is going to be bigger, right? So carrier will have this amplitude at like a higher frequency, it'll have this amplitude. At a lower frequency, it'll just have this amplitude, right? So now just by feeding it onto this sloped filter, we're making the amplitude of the carrier change with frequency, right? So that's what this is all about. There's lots of mathematical details. I think you guys have done an assignment on it. It's pretty involved because most of this stuff is done with this complex envelope as well. So you have to worry about that factor of two that pops up. But the idea is basically you just turn an FM into an AM by taking the derivative of it. And that's really the key, right? So yeah, there's lots of stuff here. And then you can see there's this positive negative slope thing at the end. It doesn't really matter, but it's this, this tends to be fairly often on the exam. So just understand the concept that you need to like by taking the derivative of a FM or just feeding it into some kind of a sloped filter, you can make the amplitude of that wave depend on the frequency, right? Okay, so that is that. And then the last thing, I had planned to spend a whole hour on it tonight, but my time management was not so great. It's PLLs, right? So PLLs are my favorite circuit. Back when I had a nice full-time job at a communications company, I just worked on PLLs all the time. They're not super important for this course, except for your lab 3 is all about PLLs. And Daniel promised that one of the um, exam questions was going to be on PLLs as well. So he did spend a fair amount of time on this. So here is the main thing with a PLL. We have some kind of a wave coming in, right? And we want to perfectly clone it using a local oscillator. So this local oscillator, it can change its frequency based on a control voltage, right? So what we want to do is set this control voltage just perfect so that our local oscillator is exactly the same as our incoming FM wave. All right. So this is just basic control theory. It's tricky initially because you see we have lots of nonlinear components. First, we have a multiplier that multiplies the incoming FM wave by our local wave. Then we have some linear stuff for like low pass filter and then our control filter. And then we have an oscillator that's basically changing its frequency based on our voltage input, right? So quite a lot of nonlinear components, but we don't in general treat this, we don't analyze it in a nonlinear form. We can linearize it. So this here, it is a multiplier, but what it's actually doing is detecting the phase difference. So remember from our trigonometric identities, when you match kind of a multiplier with a low pass filter, you end up with an output that is proportional to the phase difference between the two waves. So this we can kind of replace by a subtractor, right? And then this, once we are dealing with phase domain, this VCO, it's actually kind of just integrating our control voltage to change the frequency. So we replace it with an integrator. So the main thing with PLLs is don't try to analyze them unless you're asked to. Don't try to analyze them with the nonlinear stuff, the multiplier and the VCO. Just look at the linear models. So we can do, where's this linear model? Here we go, right? So now we can actually just treat all of these components as linear. So we have a phase of the FM signal coming in, and our phase detector is now just going to subtract the phase of phi1 and phi2, right? And then we have all of our control theory, and you see we've replaced this VCO, the voltage controlled oscillator, just with an integrator, right? Now, yeah, you can't really learn it all in one night, but this is just very basic signals and system stuff. So this is a feedback system. So the transfer functions are pretty straightforward, right? So say we want to find the forward gain. So assume that our output here is broken, so we want to find the open loop gain. So how much does this control voltage here depend on phi1? All you do is multiply it by the gain of all of these different blocks. So usually this has the KF, the phase and frequency detector gain, but here it's just a subtractor, so this will just be equal to 1. Then we get phi e. Then we're multiplying that by K naught over KV to get this error, and then we're multiplying that by this filter transfer function of h of t. So in open loop, right, basically our v of f divided, or s Laplace domain by phi 1 s is just going to be K naught over v kv times h of s, right? So that's our forward gain, basically. If we want to find our whole transfer function, remember to find transfer function of any kind of arbitrary feedback, What you do is find the forward gain. So that'll be A of S, and then divide it by 1 plus A of S times your feedback gain, right? So we've already found our forward gain. That's just the path from our phi 1 up to our V here. And then the we need to find the actual feedback gain as well. So here we see it's just going to be our integrator. So here we have, this will just be 1 over S, and this is B. 1 over S multiplied by 2 pi kV. And also it gets multiplied by oh no, it's negative feedback. So I think that's all fine. Yeah. So all we need to do now is move this here, the A value to the top and to the bottom, and then our feedback gain we put down there, and we get the whole transfer function for the output voltage as a function of the input voltage in um, in Laplace domain, right? So that's the main thing with this. It's just a linear system. You just have to do linear system flow techniques, right? So the main thing is you just need the feedback equation here. So you find the forward gain from your input to the output, assuming the feedback loop is broken. Then find just the feedback gain from your output back to the summer or the subtractor, right? And then you end up with our transfer function in Laplace domain right here. So yeah, there's a lot of kind of details that he went over, and unfortunately, you guys won't deal with them until lab 3, so it's a little bit late, but it's the main thing is just that this here three. I'd hope all of you guys have taken signals and systems. Otherwise, it's just a cruel joke to put you in a course like this. But I believe in you all. So yeah, you basically just you find the transfer function from that. You can find like the poles and zeros. And maybe Daniel was talking a little bit about second order functions or whatever. In general, you would be using this our filter here would have both a proportional and an integral term, but it doesn't really happen too much in this set of slides, so I'm not really sure, right? But yeah, as long as this can actually, basic control theory method, if you're tuning a PID controller, just set the D component to 0, and then you tune the I gain so that it doesn't overshoot too much or whatever. It's exactly the same. So this is just a super straightforward example of a control system. So as far as um, this course goes, though, I hope that this will just be enough for you guys. So just remember that the whole point of this is to make sure that our local oscillator is tuned perfectly to our incoming wave. And if it is, that means the control voltage is an indication of the frequency deviation, which means it's a perfect replica of our message, right? So our output will just be the control voltage of a perfectly locked PLL, and that'll be our demodulated FM signal. So yeah, I think that is all. Let me see if I've missed any questions here. Clan, what are some must-study topics for this other than AM, superheterodyne, and PLL? Um, I would say discriminator is a really big deal. Definitely do some frequency discriminator, complex envelope, and then beyond that, maybe just focus a bit more on some PLL stuff. But yeah, that's all good. All right, cool. So yeah, are there any questions? I think that's about it. All right, I believe in you all, even the ones I haven't seen since the first day of class, although I believe in you slightly less. Yeah, no worries, guys. Feel free to as you're studying tomorrow, just you can send me emails. I probably won't have time for office hours or anything, but if you send me emails about specific questions, I can probably get back to you. And then, yeah, just please practice the past exam and the assignments with paper and pen, right? Actually writing it down. It's not enough that it just makes sense to you in your head. Make sure that like you're quick with it because 100 minutes, you got no time to think, right? So yeah, just be nice and quick.